Look inside the physical footprint of the modern cloud, and you will find dense, tightly packed rows of server racks continuously processing data. Keeping these processors active demands a massive, uninterrupted electrical load. It also requires millions of gallons of water to cool the hardware and prevent the systems from melting down under their own computational friction. Earthly infrastructure is struggling to supply both. The financial strain is severe. Right now, many terrestrial data centers are operating at a massive deficit, losing millions of dollars every single day just to keep the lights on and the servers cool. To sustain the rapid expansion of artificial intelligence without draining the planet's remaining water and power grids, the hardware has to leave the atmosphere. We have to build data centers in space. Relocating the physical internet into orbit bypasses the resource limits of Earth. But keeping highly sensitive servers operational in a vacuum requires overcoming a brutal sequence of engineering roadblocks. The immediate bottleneck is gravity. Moving thousands of tons of server banks into low Earth orbit requires a massive payload delivery system that doesn't bankrupt the operation on launch. The heavy lift space race is highly active. Blue Origin's New Glenn rocket has already successfully placed satellite hardware into orbit, while SpaceX is continuing to iterate and test their towering Starship prototype on the launch pad. SpaceX's most viable financial path is to lock in the Starship design and use it to rapidly deploy their Starlink internet satellites. The profits generated from the Starlink network can then be used to subsidize the immense cost of launching dedicated space data centers. These AI data stations can be designed with a flat-pack geometry similar to Starlink. Hundreds of servers can be stacked tightly inside the rocket fairing and dispensed in rapid succession, sliding out into the vacuum like a massive Pez dispenser. Getting the payload to altitude is only the logistical hurdle. The moment these servers are deployed, they are exposed to the thermal paradox of orbit. Space is famously cold, with baseline temperatures hovering near absolute zero. However, objects caught in direct, unfiltered sunlight outside the Earth's atmosphere experience immediate, scorching heat that will fry an unprotected processor. The structural workaround uses the station's own power source as a shield. The server racks are tucked directly behind massive solar arrays, using the wide, flat panels to physically block the sun. These sun shields are reinforced with alternating layers of metallic structures and Kapton. Kapton is a specialized polyimide film that remains structurally stable across extreme temperature drops and spikes. Inside the shadowed server bays, the hardware generates intense internal heat from active processing. Liquid ammonia is pumped through the system as a coolant, absorbing the high temperatures and drawing the heat away from the delicate AI chips. Pushing this waste heat away from the servers keeps the data center alive. It also perfectly isolates the exact raw material needed to generate the station's independent power supply. Traditional solar arrays alone cannot capture enough sunlight to satisfy the immense, constant electricity demands of a continuously running AI server farm. The gap in power is closed by routing the captured waste heat into a Stirling engine. A Stirling engine is a heat engine that generates continuous mechanical power by rapidly compressing and expanding a gas at two drastically different temperatures. This diagram shows the thermodynamic loop in action. The engine achieves massive rotational efficiency by exploiting the extreme contrast between the boiling waste heat of the AI server on one side and the near absolute zero void of space on the other. The mechanical energy produced by that extreme temperature gradient is converted into electricity, which is then fed directly back into the AI processors. Engineers can also direct the outer cooling panels to emit subtle thermal radiation. This allows the panels to act as low-thrust photon engines, gently correcting the data center's orbital trajectory over time. The thermal and power loops are highly efficient, but launching thousands of heavy, self-sustaining server blocks into the exact same orbital lanes dramatically increases the risk of Kessler syndrome. Kessler syndrome is a theoretical cascade where collisions in orbit create so much fast-moving shrapnel that space becomes entirely impassable. Without a proactive debris management strategy, deploying endless arrays of data centers will guarantee a catastrophic chain reaction of orbital collisions, trapping humanity on Earth. The mitigation strategy requires launching specialized, highly maneuverable space tugs alongside the server banks, using the exact same high-volume rocket deployment. Their sole purpose is to actively hunt down defunct satellites and stray metal. To avoid the massive cost of launching fuel from Earth, these space tugs are built to literally ingest the space debris they catch. By consuming the dead satellites, these tugs clear the orbital shipping lanes. More importantly, they convert the hazard itself into an unlimited supply of ammunition for their own propulsion systems. This schematic details the tug's mechanics. Magnetic coils and microwaves melt ingested scrap into superheated plasma. This highly conductive gas of stripped electrons is gripped by magnetic fields and accelerated as thrust, giving the drone force to push dead satellites into a graveyard orbit. With the debris fields actively cleared, an expanding armada of space data centers can safely hold their positions. Spanning thousands of miles, their massive combined solar arrays and cooling panels will function as a physical parasol, passively blocking a fraction of incoming sunlight. Moving our computational hardware into orbit solves the severe energy and water crisis restricting modern AI. Through sheer scale, it also constructs a permanent layer of orbital infrastructure that actively cools the Earth below.